Hello everyone, welcome to our talk. My name is Jianrong from 360 Alpha Lab. Today my colleague Zhou Peng and I are going to share an exploit chain to remotely root modern Android devices with only two vulnerabilities. This work is also contributed by Han Hongli and Wang Xiaodong. We are all security researchers at 360 Alpha Lab. Our team mainly focuses on mobile security, including TiYunZong, Kernel, applications like browser and so on. We have reported more than 400 vulnerabilities to top vendors and won the highest reward of the ASR program in 2017 and Google VPR in 2019. We also successfully pumped many targets in Pang and Tianfu Cup contests. This talk mainly consists of four parts: a brief review of the remote attack surface of Android devices, followed by the overview of our exploit chain. Then we will detail the root cause of these vulnerabilities and share the exploit strategy. At last, we will present a demo of remotely rooting a Pixel 4. So let's get started. For mobile device, there are usually two types of entry points for non-physical attacks. Technologies such as Bluetooth, NFC, and baseband allow mobile for remote communications, so attackers can send malicious traffic to the connected device. This kind of attack often doesn't need user interaction, but is more limited in range as compared to the attack over the internet. Technologies such as mailing, instant messaging, and web browsers can be targeted over the internet and have a large attack surface on their own, as they often must deal with executing application logic, rendering of web pages, and other underlying protocols. A typical remote root solution is to use the browser as the entry point to obtain code execution capabilities in the render process. Since this process is highly sandboxed, attackers need to chain other bugs for escaping the sandbox and elevating privileged to system user or root. Since the last time our team discovered the TiYunZong exploit chain to achieve one-click remote root on Pixel 3, we once again set off towards this goal, targeting new Pixel devices with latest updates. We named the new exploit chain Mangkhut and reported to Google in July 2020. So why Mangkhut? In September 2018, a typhoon named Mangkhut formed on the Pacific Ocean. At about the same time, a powerful vulnerability was introduced into the Android kernel, which we used in this exploit chain to escalate from the highly sandboxed process to root. While the typhoon Mangkhut caused extensive damage in the real world, the vulnerability may show its destructive power in cyberspace. The exploit chain only consists of two bugs, a type confusion bug in Chrome, and a kernel bug which can be leveraged to escalate from the highly sandboxed process to root. This chain affects a wide range of devices running multiple versions of Android system, and it is the first reported exploit chain to remotely rooting Pixel 4 and acknowledged in Google VRP annual report. So here is the first step, RCE in Chrome render process. This bug exists in the promise all-settled built-in function of Chrome's V8 JavaScript engine. Let's take a look at the function first. It accepts an iterable object as parameter in which each member is a promise. The function returns a promise immediately, and the output promise is fulfilled with a just array only after all the given promises have settled. The array contains objects that each describes the outcome of each input promise. Here is an example. The input contains two promises. One is fulfilled with value 1 and the other is rejected with error 2. Promise all settled returns a new promise as its output, and we call the then method on it. Since all input promises have settled, we get the result array in a callback. The result array contains two objects at index 0 and index 1, describing the output of input promises. From the perspective of code implementation, V8 needs to manage a result.js array and allocate some space for storing the outcome. For example, when the first promise is fulfilled, V8 stores the result in the fixed array at index 0. More importantly, user could get the JS array only after all the given promises have settled, which means if there is any promise stays in pending state, V8 would not return the JS array to user. So how does V8 know all promises are settled? This requires a cross-context variable named remaining elements count. It is initialized with the number of input promises and is decreased by 1 when a promise is settled. When it becomes 0, V8 would return the result array. According to the specification, a promise is said to be settled if it is either fulfilled or rejected. So either resolve element function or reject element function will get called depending on the promise is fulfilled or rejected. And both of them will eventually call promise or resolve element closure function. This is where V8 stores the promise outcome to a result array and counts down the number of remaining pending promises. This function is implemented using Torque language, whose syntax looks like TypeScript. We can see that it reads remaining elements count from the function context slot first and subtracts 1 and saves it back to the context. When remaining elements count becomes to 0, the function will return an array of objects as a result. Normally, add the resolve element function or reject element function should only be called once at most, which means turning a pending promise into a fulfilled or rejected state. But what if we could call them both? The remaining elements count would be decreased by 2, and it would become to 0 when only half of input promises are settled. As a result, user would get the result array at an earlier time. Here is a proof of concept about how to get these two functions. We call the promise or settled function on our custom defined class. V8 would call the resolve method to get next promise, and try to call the then method defined on the next promise. We can see that resolve element function and reject element function are passed as parameters. That's how we get these two functions, and we can call any of them whenever we want. So this may result in type confusion if the attacker gets the result array and there are actually still some input promises needs to process. V8 believes that the backend store is always a fixed array, while we can change it to a number dictionary. Suppose the first promise is settled, then V8 tries to write the result to a fixed array at index 0, but it actually corrupts the metadata field of a number dictionary. The approach to achieve out-of-bounds write seems very straightforward at first glance. When V8 stores a value to the result array, it first checks whether the index is inbounds of the array. If the index is smaller than the array length, V8 just stores the value in its backend store. With type confusion, even though the array length could be a large number which can bypass the inbounds check, the size of number dictionary may be small. Thus, an out-of-bounds write could be triggered at line 8. Unfortunately, this would only crash the process, because there exists another out-of-bounds check when Torque compiler generates code like that. So we want to figure out another way. Another constraint is that we cannot control the content of data to be written precisely. It is always an address of a JS object which describes the outcome of the settled promise. Since the out-of-bounds write is not working, so what else is valuable to overwrite inside a number dictionary? The capacity field indicates the maximum number of entries the dictionary can have, which seems to be a good target. By overwriting this field with the address of a JS object, which is usually a relatively large number, we can trigger out-of-bounds access through the victim array. However, this offset of out-of-bounds access is not predictable because of the way of V8 read or write a dictionary. After more research, we choose to corrupt a max number key field, which converts the type confusion bug to another out-of-bounds read problem. Max number key indicates the maximum valid index of number dictionary, and more importantly, its least significant bit indicates whether there is a special element on the array, such as accessors. For example, if we define a getter at index 0, the array is treated as a special array because it will trigger user-defined codes while accessing the element. If the bit is set to 1, it means the number dictionary has no special element. But by exploiting the type confusion bug, we can corrupt this field with the address of a JS object. And the least significant bit of any heap object address in V8 is exactly 1. So taken together, we can make the special array not that special. So the next step is to find a place where we can use our special array to gain more powerful ability. In this case, the array prototype concat API would do the trick. In iterate elements function, it calls has only simple elements to check whether there are accessors on the receiver's elements. As described before, our special array could bypass this check so that get element would be called in the fast path. However, there are in fact accessors defined on it, which we can call back to our user-defined JavaScript codes. And out-of-bounds read would be triggered if the array length has been changed to a smaller value while the iteration continues. So we have successfully converted the type confusion bug to another out-of-bounds read bug. And the rest of the work is not hard to achieve code execution from this OOB read condition, so I'm gonna to give a brief introduction here. First, we can leak the address of an array buffer's backend store, and second, fake a double JS array in this array buffer. Then, trigger the out-of-bounds read again to retrieve the reference of the fake array in JavaScript codes. Fourth, use the fake array to modify a victim array buffer's memory layout for arbitrary read and write. And next step is to write shellcode to a WebAssembly code URL, and finally calls the WebAssembly function to execute shellcode. Now we can compromise the Chrome render process, and I'll hand it over to Zhou Peng to show you how to escape the sandbox to root privilege.
Thanks, Rong. Next, I will share with you how to escape from Sandbox to root with the Bender bug we found. First, I will introduce why Bender was chosen as a research target, and then the cause of the bug. After we found the bug, in order to verify the usability, we first exploited it in an untrusted app environment. This part will be introduced in the third part. After proving the usability of the bug, we further complete the privilege escalation in the sandbox environment. This part is also one of the most interesting links today. Finally, I will show you a demonstration. In the TiYunZong exploitation, we used 3 vulnerabilities, 2 of which were used to elevate permissions from sandbox to root. This year, we set out again and try to use only one bug to achieve this. In Android system, Blender is one of few drivers that can be accessed inside the sandbox. So its vulnerability can be directly used for sandbox escape. This time, we looked at the vulnerability mining target on Blender. In fact, the Blender module has always been a hot topic for security researchers. Since the water drop vulnerability has found multiple bugs have been found in Blender driver. For example, Project Zero team found one in 2019 and the Blue for Stack team found one in 2020. Statistics show that there is a bug for every 1,000 to 1,500 lines of code, and the Blender save file totals less than 6,000 lines of code. So we have to think about one question. Is there still such serious security bug? Of course, the answer is yes, and that's why we're here today. The Blender root is like a nuclear warhead and the browser RC is like a launchpad. And the combination of these two will become an intercontinental nuclear power. Next, I will introduce in detail how to use a Blender vulnerability to achieve stable kernel arbitrary read and write and finally get root in the sandbox. A complete Blender communication process has a total of 4 steps. First, the client sends the BC transaction to the kernel and the kernel forwards the request to the server. Then the server replies BC reply to the kernel after processing and forward it to the client after processing. One point we want to pay attention to is that when sending the Blender object, a Blender load object in the kernel will be created. The Blender work it contains will be inserted into the thread to linked list, and the reference to the Blender node will also be inserted into the progress by node tree of target process. Normally, client can process Blender workload type work by Blender thread rate function. However, there is another way to process Blender work, which is by sending Blender thread exit or command to trigger the Blender release work. But this function has a risk problem. After W is removed from a chain, there is a low log protection anymore. So there is a risk window before accessing W type. If the Blender work is released between this window, it will cause UEF problem. Then we take a look at when Blender work is freed before Blender release work. From this picture, we can see after the server receives and processes the Blender object, it will send BC buffer free command to the kernel. After receiving this command, the kernel will find the corresponding Blender load according to Blender rave and decrease the reference counter. If it is down to 0, the Blender load will be released. If the read succeeds, it will cause the Blender load to be released before accessing W type. So how can we exploit this UEF vulnerability? The key point of the UEF vulnerability is use. In the Blender release function, there are 2 branches that can trigger the key free operation. So this UEF problem can be converted into the double free problem if we can control the W type. What we can do with a double free? We can hijack free list to allocate a specific memory and write any content into it. That's interesting. We can use it to modify the swapper to achieve KSMA attack. Next, I will introduce the details about this process. There are 4 steps to complete this thing. For a UEF problem, the first step, of course, is using heap trace to modify the content of a free buffer. Because we want to launch KSMA attack, kernel-based address leak is needed also. And then we'll talk about how to hijack free list and achieve KSMA attack. It's not easy to do heap spray. As shown in the disassemble code, from unlock to use, there are only a few instructions to execute. So the race windows was very narrow. Thus, it's very difficult to change W type by doing heap spray. This is a similar problem we have encountered when exploiting water drop vulnerability. Similarly, there are only a few instructions between unlock and use. The race window is also very short. So, how to increase the success rate of race? Through analysis, we found that the wake up queue function is used in the mutex unlock operation. Let's have a look at its function. We can see wake up queue eventually calls try to wake up other thread, which means the mutex unlock operation will actively give up the CPU. Therefore, we can bind multiple threads into one CPU and then use mutex lock to wake up other race thread. By this method, we get nearly 100% success rate. But same method cannot be used here because spin lock is used in bender decaying workhead, and when spin lock is released, it will not wake up other thread. That is to say, it will not actively give up CPU. Actually, there are two main ways to improve the success rate of heap spray. The first one is the old school method. Just bet CPU and increase number of heap spray thread. Under frequent scheduling, you can always find a chance in the race window. The second one is special. Increase the number of band objects can also increase possibility. Because band release work also use a loop to process band work. More band objects means more chance to create race scene. And another advantage is that spray figure will enter default branch and won't result in any system abnormalities. As for the heap spray method, we use send message. And once the heap spray is completed, a key-free operation with an offset of 8 will be triggered. And if we release the slab copied by send message, we can build a double phrase scene. After solving the spray problem, our next task is to need kernel address. Let's take a look at the method of converting the double phrase first. When double type is tempered with transaction complete by heap spray, the operation of key-free W will be triggered, and the offset of band work in band load is 8. So a double phrase with a third offset will be formed. This page shows the whole process of converting the UEF bar into a double phrase problem. The first step is to use send message to do the heap spray. If the race succeed, A plus 8 will be treated as a heap and released. First, after calling receive message, A will be released. Therefore, A and A plus 8 exit on frame list at the same time. And there is overlap on memory area. Then let's have a look at the seg file structure. Seg file is a common structure type of virtual file system in Linux. Multiple files in prog directory is managed as seg file. For some special seg file like prog CPU info, OP field is a global structure address, which can be used to Linux kernel-based address. So, how to nick the OP pointer? There are many 5 steps. The first step, of course, is to trigger the bark, and then we need to copy A plus 8 with band load. And then we call receive message to release A. Now we can copy A with seg file and call band thread read to read PTR out, which is the OP field of the seg file. The following content is relatively simple. Similar to the Linux kernel address, radius hijacking can be roughly divided into 6 steps. First step is to spray with send message. After the bug is triggered, A plus 8 will be released, and then we call receive message to release A. Currently, both A and A plus 8 is on the free list. The next steps are very interesting. Then we reallocate A back by sending message and write X into it. Now free list head is A plus 8. Then we call send message again and get A plus 8 back. Now free list head X is X. Send a message again. We can write any content into the address X. Now the next step is to launch KSMA attack. There are a few things we need to pay attention to. Kernel code segment physical start address is 820.840 and KSMA attack's basic map size is 1 GB. So fake page table use address 870 and offset 840 is needed when read or write kernel code. After each round of attempts, it is necessary to check whether the page table has been successfully modified. Because we write exploit in C, we use set jump and long jump to process exception. If an exception is triggered, it means swapper hasn't been modified yet. According to the previously shared exploit schema, we successfully completed the local privilege escalation. After proving the usability of this vulnerability, then try to complete the privilege escalation in the sandbox to take full use of this power of this vulnerability. There is no doubt that there are many restrictions in the sandbox. The first one is limited syscore, which means we can't ban CPU anymore. Also, file and devices access is strictly restricted, not to mention writing files. And Chrome Sandbox enables its own BPF rules. The next one is that Chrome is 32 bits, but kernel is 64 bits. It has two effects. The first is that it will cause syscore compatibility problem. The second is that KSMA attack is not working. Therefore, when we try to pull the local schema to the sandbox, we encounter two severe challenges. The first one is load balancing CPU. So, triggering the bug will be very difficult. The second one is low KSMA. It means we have to find a total new solution which no one has used before. But luckily, send message still can be used to do heap spray. These two limitations forces us to find a new solution, which is very challenging but interesting. We decided to solve the first problem first. Corresponding to heap feng shui, we want to introduce a new concept called CPU feng shui. We think there are two factors that determine the success rate of a race. The first one is time slice. It's not hard to understand that reducing time slice can increase the possibility to switch CPU in the race window. Otherwise, increased waiting schedule time can increase the possibility to let code block in different thread execute in a specific sequence. Based on these two factors, we found some key methods of CPU feng shui. The first one is creating multiple petty threads to increase CPU node. Petty thread does nothing but makes CPU very busy. The second one is to adjust thread priority to influence thread time slice and wait schedule time. The last trick is to get currently belonging CPU is read from proc-state file rather than the get CPU. This is also helpful for us to do heap feng shui. After solving the first challenge, we start to solve the second one. Before looking for a new solution, we decided take a new look at historical exploit examples that have stable arbitrary reading and writing, and looking for some inspiration. From these two methods, we found something interesting. That is controlling the pointer to get arbitrary read and write. Let's keep going. The common elements of these two methods is memory share. And that's why it's more interesting. It has two elements we just mentioned. Through the analysis of these cases, we found two interesting basic elements. The first one is memory share, which means to use the shared data to achieve arbitrary read and write. For example, if structure A and structure B overlapped, and we can use pointer in structure B to read or write, then we can control PTR the pointer through structure A to get arbitrary read or write. Different from the first element, the second element does not focus on how to control the pointer, but to combine the code logic to achieve stable arbitrary read and write. Based on these two elements, we found several structures. After they cooperated with each other, it was like a fusion of chemical reaction, bursting out huge power immediately. First, let us have a look at the HMAP interface. This structure is saved as a pointer to file private data. The getName function of the HMAP interface can read a section of memory from the kernel. If the private data pointer can be tampered with, it can read content from any kernel address. Similarly, it can use the setProductMask function to modify the content of specified address. But due to the limitation of code itself, the most practical usage is to write 0. And with the help of the setName function, after writing can be also achieved to some extent. Now, let's take a look at the circle file. The first element of circle file structure is the buff pointer. The data can be read from buff pointer to the user mode by calling the circle read operation. Once the buff pointer is tampered with, it means we can read data from any address. Writing is more interesting because the conf file is the only circle file with controllable content and is not subject to permission control. The way to modify its content is to modify the thread name. Corresponding operations in the kernel is divided into two steps. The first is to save thread name to the task com. When a user tries to read content from com, the kernel will call the com_show function to write content of task com into the memory pointed by circle file buff through circle print. If the buff pointer can be tampered with at this time, the arbitrary address write is achieved. If item cannot achieve arbitrary read or write, but it can be used to repeatedly write arbitrary 8-byte data to the kernel fixed memory, which is very useful. I have already introduced 3 structures and the related functions that can be used to achieve arbitrary read and write. So how to achieve this target? At first, what we think of is to use HMAP. As the PowerPoint shows, we first need to modify private data 1, which makes us be able to modify the private data 2. Then we can use file 2 to read or write target memory. However, the conditions that need to be met are 2 nicks and 1 write. It's difficult to meet, right? So, is there a better solution? Combining the characteristics of this solution, this vulnerability, we finally found an almost perfect solution. First of all, the size of these 2 structures is exactly 128, so it can be allocated on the same page. Because there is an 8-byte offset when a vulnerability is triggered, if you can make these 2 structures adjacent when you allocate them, you can make data field of equal item overlap with the buff field of circle file. Once setup is completed, stable arbitrary read and write can be completed without any leak or write condition. It's either after plan is determined. only a few steps are needed. First step is to prepare some holes before Circ5 doing heap feng shui. The second step is to fill these holes with bender load. But here is a little trouble. A OP structure is allocated before Circ5 and it cannot be deallocated separately. The solution is to control the allocation order. Through continuous testing, we found that eventfd can help us accomplish this task well. It has several characteristics. First, it can be accessed in the sandbox, and closing eventfd will immediately deallocate the slab. Control the closing sequence of eventfd so that slab allocation can be carried out in a specific order. As shown in the PowerPoint, we firstly close the event of D3 and then close event of D1. And then the order of the heap blocks in the free list will be event of D1, then event of D3. In fact, this corresponds to the allocation order. Now, after the preparations, we go to create the seg file, and the structure corresponding to the OP field can be separated from the seg file. At this point, just close event of D2 again to leave the hole before seg file. Now, we can fill the holes with bender load. Next step is trigger key-free C+8 and allocate C+8 back for the equal item. Now we have the ability to read and write at any address, but we still need to leak the kernel address before we can continue. However, it is very interesting that we only need to replace the equal item with bender load. It's not difficult to find that the last field of bender load is doubly linked list, which points itself when initialized. So when we overwrite the buff pointer with the pre pointer, content after the bender load can be leaked. Usually, the last step is to close the SNX and set UID GID to 0, but it's not enough yet. When running exploit, we failed to reverse a shell after closing SNX, and there is no way to bypass BPF directly. So when we disable BPF, so we have to disable the BPF. Setting filter to long won't work. We have to set in the filter to the penultimate element to turn off the BPF. Finally, I would like to point out some shortcomings of this schema. Because for the size of Circ5, bender load, equal item structures are exactly 128. But these structures may differ in different system versions. Once the size of the structure changed, the current plan may fail. The second point is that we still need to adapt this as Linux enforcing. So could it be done automatically with the ability of arbitrary read and write? I would like to leave this question for you. Finally, let me show you a demonstration we have recorded. At first, we will check the Chrome and Android version. After check is done, we will use the Chrome browser to access an attack page. As you can see, we reversed a shell, and this is a root shell. Now we use this shell to install an app and start it. First, we need to download it from the internet and call pm install command to install the app, and use the am command to start the activity. Let's take a few seconds. As you can see, an app is installed and started. Okay, thank you. Any questions?